recording it, and then everyone else can watch the recording of it, and I'll never have to do it again. All right, so this is 4.7, question number 10 on my math lab. Okay? And we're asked to evaluate this limit here. Hopefully by the time, and if you're not comfortable with these problems, this is a bad problem to learn the technique on, right? This is an extremely challenging question, and it's the wrong one to be learning how to deal with indeterminate powers on. Okay? So, I'm assuming then you've already dealt with a few indeterminate powers. And I know this is kind of early on in the My Math Lab, but we did some in class, these indeterminate powers in class. And you can jump into some other indeterminate power questions that aren't so intensive as this one.
Actually, I don't think it's number 10.
Oh, okay.
It's number 20.
Number 20. Thank you. Great. Great. Okay, great. Number 20.
Yeah.
Okay, good. So even in the My Math Lab at that point, you will have experienced some other indeterminate powers, because this one is extremely tedious. All right, let's first, and if you're not doing this, folks, then you're doing the Hopital's rule wrong. Let's first identify the indeterminate form that this has. Okay. Well, what is my base approaching as x is approaching 0 from the right? Yeah. Okay. Sarah says we're approaching 1. Okay. That's that limit. That's the limit that we've seen before. If you've forgotten that, folks, what is the limit as x approaches 0 of the sine of x over x? If you forget this, now you can do it, because this is indeterminate form 0 over 0, right? So you can now use the Hopital's rule on this, and you get the cosine of x over 1, taking the derivative of the numerator or the derivative of the denominator, which is no longer indeterminate, which is just the cosine of 0. And what is the cosine of 0? 1. Okay, so I never actually proved that limit to you. Okay? This is a justification of it. It's not actually a proof. It's a justification, though. Okay? All right. So anyway, as Sarah said, the base is approaching 1, and then what's my numerator approach, or what's my power approaching? Yeah, because it's 8 over an arbitrarily small number, arbitrarily small positive. So this has the indeterminate form 1 to the infinity power. Okay? So, well, I mean, this is a challenging question. If you got hung up on this, well, we'll get through it. Okay? But what I do expect you to know is, how do you deal with an indeterminate power? That's worthy of a flashcard. When I have indeterminate form 1 to the infinity, what's my strategy? What is my strategy? To give up? No? Yeah, we're going to take e to the natural log inside the limit. Okay, so this is equal to the limit as x approaches 0 from the right of e to the natural log of the whole expression, sine x over x to the 8 over x squared. Okay. In this next line, I'm going to do 2 steps at once. What are the 2 steps that I do? All right, so at some point I'm going to pull this exponent outside the ln. I'll do that in just a moment. What else am I going to do? We've got to pass the limit through this continuous function. Okay? So we get, this is equal to e to the limit as x approaches 0 from the right of, and then we'll pull out the power, 8x squared times the natural log of sine x over x. So I did 2 steps at once. The first step was to pass the limit through the continuous function. Okay. That's a step that, you know, we haven't done a whole lot in this class. Let me give you this example. If I looked at the limit as x approaches, say 1 of the tangent of x squared minus 1 over x minus 1, because tangent is continuous at 1, I can pass this limit through and say that's equal to the tangent of the limit as x approaches 1 over x squared minus 1, of x squared minus 1 over x minus 1. What did I do there? I passed the limit through the tangent function. Can I always pass a limit through a function? Can I pass a limit through any function I want?
No.
No. What does it have to be?
Continuous.
Continuous. Okay. Amy?
When you passed out the exponent, it was 8 over x squared.
Oh, good catch, good catch, good catch. Sorry, folks, everyone see my error? Okay, this should be 8 over x squared. Great. Okay, good catch. Okay. So now, let's see if we've gotten anywhere. Let's identify the indeterminate form, not of the entire expression, but just of the limit. What's the indeterminate form of this limit? Well, the first factor, as x is getting large, is approaching what? Oops, sorry, the first factor as x is approaching 0 is approaching what? Infinity, right? Because we're approaching 0 from, well, this might not have had a, yeah, we need a 0 from the right on it.
Yeah.
I can't remember if we need that 0 from the right on it or not in order to analyze this. That's all right, that's all right. We'll, if it's there, great. If it's not there, we'll be okay. All right.
It's there.
And then what is the second factor approaching? So we said the sine of x over x was approaching what? 1. So the natural log of an argument that's approaching 1 is approaching what? 0. So this now has indeterminate form, infinity times 0. Did we get anywhere? I would argue we did, because the hardest indeterminate form to work with is is an indeterminate power. Now we're down to an indeterminate product. But what's our goal? To do Hopital's rule, we need an indeterminate quotient. Right? So I think you should always be stopping to identify what indeterminate form you're working with, because that gives you guidance as to what you want to do next. What was our trick for an indeterminate product? Yeah, bring one factor down and then invert it. Okay. How did it go when we tried to bring natural logs down and invert them? Not so good. So let's bring the polynomial component down and invert that. So this gives us e to the limit as x approaches 0 from the right of the natural log of the sine of x over x divided by x squared over 8. Okay. This is horrible on the eyes, folks, this big nasty expression here, which is partially why my math lab will just stop writing this e until the very end of the problem. And I really don't like that. Okay, so I'm going to always write the entire expression because that's how I think you should do math. Okay, but my math lab will just say, let's just peel this exponent part aside and let's just work with the exponent for a while. Okay, but I think you should be always writing the whole expression. So that's what I'll do, but just know that that's how my work will be a little bit different from my math labs. Okay. Okay. So let's identify the indeterminate form. See what we've got. The numerator is still approaching 0. Now what's my denominator approaching? Meaning this fraction right here, what's it approaching? It's also approaching 0. At long last, we've got the right indeterminate form. So I've had some students coming by and they were getting help and they weren't identifying the indeterminate forms along the way. Well, you don't know what to do if you don't identify the indeterminate forms. Okay. At this point, I can, if I want, do what? Apply Hopital's rule. So we will go ahead and do so. And this is where this starts getting messy. Okay. By the way, let me make one comment. At some point I'm going to take the derivative of x squared over 8. Please, folks, that's the same thing as 1/8 x squared, right? So I'll think of it that way when I take its derivative. I'm not going to think of it as a quotient rule. Okay, so applying the Hopital's rule, here we go. We get e to the limit as x approaches 0 from the right of 1 over the sine of x over x times, and then I've got a little quotient rule here. So here's my bottom, derivative of the top, minus, there it is, minus the top times the derivative of the bottom, all over the bottom squared. That was just the derivative of the numerator. all over, what's the derivative of the denominator? Well, if I'm thinking about it as 1/8 x squared, when I take the derivative of 1/8 x squared, I get 1/4 x. I'm usually not rude, but doggone it, that is an ugly expression. All right, let's keep going. I now need to clean this up for a few steps. I'm just going to take a few steps to clean this up because I've got fractions inside of fractions and factors that will cancel. Let's see what happens. So all this is for the next couple steps is cleaning up. Okay? So this gives us e to the limit as x approaches 0 from the right. Now, I'm going to first go ahead and it's going to take me an extra line, but I'm going to go ahead and invert this fraction right here, right? So it's 1 over the sine of x over x is just x over the sine of x, right? Inverting and multiplying. So that gives me x over the sine of x times x cosine x minus sine x over x squared, all divided by 1/4 x. All right, it's a little less ugly. Now, I notice that I can factor, or I can cancel this factor of x right here with one of these factors of x right there. Can I cancel this x with this x? No, because I would need an x in all factors to be able to do something like that, and I don't. Okay? So anyway, cleaning this up one more time, we get e to the limit as x approaches 0 from the right of x cosine x minus sine x, all over here I've got the product between sine x and x, so that gives me an x sine x all over 1/4 x. Okay? I've got one more step to clean this up. Okay? There's two different ways I can think about this. The easiest way to think about this is to say, hey, I've got fractions inside of fractions. Let's clear out the smaller fractions. How am I going to do that? Well, I'm going to multiply this big numerator by x sine x all over the big denominator by x sine x. Can I do that? Sure, I'm just multiplying this expression by 1, which is always legal. The reason why I do that is because now I can cancel those two factors, and so we end up with e to the limit as x approaches 0 from the right of x squared cosine x minus sine x, minus x sine x. Nope, I'm sorry, that's, folks, I drew this and I missed, this whole expression canceled. I didn't, did everyone see my mistake? I didn't draw the cancellation mark through the x, so I thought that x was still there, so I was doing more work with it. Sorry. This is x cosine x minus sine x all over 1/4 x squared sine x. We'll turn this frog into a princess yet, right? Like the fairy tales. Right? Where we take this ugly expression and make it bring out its inner beauty, or whatever they do. All right. So, this still has indeterminate form 0 over 0. We didn't get anywhere as far as the indeterminate form aspect went, but at least we don't have a natural log anymore. And you could argue, you know, at least now we've just got a single fraction. So I think things seem a little bit better. We'll take the derivative again and see where we're going. Or sorry, we'll take Hopital's rule again and see if we're getting anywhere. So applying Hopital's rule a second time, notice in my big numerator, I'm going to have to do a product rule for this first factor. This requires a product rule. So that gives me first derivative of the second plus the second times the derivative of the first. That was for this product rule right here. And then I've got minus the derivative of the sine of x, which is minus cosine x. All over. Now I'm going to have to do a product rule on this guy right here. So we do 1/4 x squared, the first, times the derivative of the second, plus the second, which would be sine x, times the derivative of the first, which would be 1/2 x. All of that was this product rule right here. Right there. Okay? I never want to do this problem again. All right. Will you have a test question this hard? No. No.
Thank you.
I don't want to grade it.
I don't blame you.
I don't want to see where you went wrong. All right. What do we have here? Well, let's see here. Oh, let's take one line to clean this up slightly. We get e to the limit as x approaches 0 from the right. Notice I've got a cosine term right here that cancels with that cosine term there. This gives me minus x sine x all over 1/4 x squared cosine x plus 1/2 x sine x. This is one of those really long Disney movies. Holy smokes. All right, this still has indeterminate form 0 over 0. Right? The numerator goes to 0, the denominator goes to 0. But I have hope, having done a few of these before, that we're getting pretty close. When I go to take the derivative of this x sine x, I'll do a first derivative of the second, no good, plus a second, sorry, here, somewhere it happens, where is it? Oh, sorry, I can do one more step to clean this up. That is true that it has the indeterminate form, but let's notice that we can factor out a common factor of x. So we get minus sine x over 1/4 x cosine x plus 1/2 sine x. Does everyone see that? Each one of these terms had a common factor of x. For those of you who have cancellation problems, I didn't just cancel this x with this x. I took a factor of x out of every term in the denominator and canceled it with the term in the numerator. So this still has indeterminate form, 0 over 0, but now I have hope. When I go to do the chain rule or the product rule with this piece right here, I'll eventually get a cosine term by itself. And the cosine of 0 is not 0. Same thing when I take the derivative of that term, I'll have a cosine term by itself, so that won't go to 0. So I feel like even though this is a disaster, we're one step away from cleaning it up. Okay? All right, here we go. This is equal to e to the limit, as x approaches 0 from the right, of minus cosine x all over, here I've got a product rule, first, derivative of the second, plus the second, there it is, times 1/4, the derivative of the first, plus 1/2 cosine x. Abby already sees the end of it. She's entering in the answer in my math lab as we speak. All right, I see the end of it too, right? We can now evaluate this limit. How? Through direct substitution. So this gives us e all to the minus 1 all over 0 plus a quarter plus a half. Which is equal to e to the minus 1 all divided by 3/4, which is equal to e to the minus 4/3. Okay. Let me show you this my math lab question. Because besides getting the answer, there's the added insult, I feel like, that you don't know what baby step it wants you to answer. And I know that you guys have been dealing with that quite a bit in this section. I'm looking into how to fix that for subsequent courses. That doesn't help you, I know. But that is a frustrating aspect of this. Okay? You don't know what baby step it's looking for, which is a pain. I understand.
Especially when you do all the work.
I agree. I agree. So, we got different numbers now. That's all right. So let's see here. We wanted to take the natural log of both sides to rewrite this as, and then it wants this, I believe the way it wants this as, then e to the, so folks watching this video, I'm not sure. You do the work that we just did. The point is that for this baby step, they just want you to go ahead and actually enter in the constant that you got all the way through the problem, which is kind of a silly baby step. So I'm just going to have it say, I'm just going to do my 3 attempts. I'll get it wrong, and we'll see what I mean by this. So here they want you to enter in just the constant that you would get in the limit. Does that make sense? Which is your answer. So then the next step is, well, what's the answer? And it is this e to the 13/6 in this case. I didn't have time to redo the problem. So we just get e to the negative 13/6. So no, for those of you at home watching this, this is the same expression as you got as your final answer. So for this one being a baby step, it's not really a baby step at all, which is exceptionally misleading at this point in the question. All right, so folks, hopefully that gives you an insight as how to do that problem. Give it a shot. Okay, if you don't get it right, that's not a big deal. Okay.